speaker is Ramis Movassagh, and he will be talking about entanglement in quantum.
All right, thank you. Thank the organizers for being here. It's not my first time here, but every time I come here, it's really fantastic. Especially thank you, Vladimir. And Simon Center has always been exciting, so it's nice to come back. All right, so the plan of this talk is that first I tell you some things that I will not talk about, but they're interesting, so I'll just quote the answers. About the generic aspects of entanglement and gap. Then I'll tell you about this Modskin walk Hamiltonian, just review it. I've given a talk here before on this Modskin states and the S-colored-Motzkin walks that Israel also talked about yesterday. So there is a video lecture of it online in case you're interested to get all the details. But I'll review it quickly because then I can use that because there are new proposals, in particular one by Solberger and Korapin sitting in the audience, Fredkin Spin Chain, that I have some new results on I want to report. So the talk is going to, the level of technicality is going to be an increasing function. All right. So first of all, congratulations to quantum community for yet another Nobel Prize. And quantum mechanics deals with Hermitian matrices. So we have Hermitian operators and Hermitian matrices. It includes everything we do. So yeah, that was the introductory slide. So appropriately, so since they're Hermitian, the eigenvalues are real. They can be ordered, all right. And E0 and E1 are the ground state and the first excited state, or what have you. But under this set of assumptions, you can ask some very meaningful questions. So, for example, the first question you can ask is, what are some generic properties of such operators? That's a very, open-ended, minimal constraint. But that's mostly a question of mathematics these days, random matrix theory. For example, we know that for some very generic ensembles, the eigenvalues follow a semicircle law. It should really be called a semi-ellipse law, but it looks like a circle. It's cooler to say semicircle. The edge statistics follow Tracy-Witham laws, and their algebra is described by free probability theory. A lot of things are known for these generic matrices. And it's a very active frontier in pure mathematics. I mean, these results are, the level repulsion was proved in 21st century. Actually, there's been a couple of years. So it's a very active frontier. But it's of little use for us to some extent. So, you could ask out of all these possible Hamiltonians, which ones are physically relevant? Perhaps there's some structure we're going to impose on these Hamiltonians besides just the fact that they're Hermitian. And it turns out that in quantum many-body systems, most of the interactions are local. For example, if you have two particles, there's a nearest neighbor interaction. And we don't care about all the eigenvalues. We don't care about the fact that the eigenvectors are all hard distributed. What we care about is the first energy state, we call it the ground state, and the distance to the second energy state, which we call the first excited state, and the corresponding state. So the gap, the ground state properties are of paramount importance in quantum many-body systems. Often macroscopic systems reside in the ground state. So this is the second question you can ask, which is physically relevant. And then you can ask, well, what are the generic properties within this low-dimensional subset of all Hermitian matrices? So within all these physically relevant, after you impose the necessary structures, what is generically possible? Okay? So I'm fascinated, actually, by all three of these questions. It touches on my various research agenda, but I won't be talking about everything. But I'm happy to discuss any one of these with you during this visit. So, this is a local Hamiltonian. So I'm going to tell you about everything I'm not going to tell you about today. So it's a local Hamiltonian in whatever dimension. So we know, so Bruno also talked about this. Intuitively, to me, it was always clear. To some people, it was clear. To many people I talked to, it was not clear. They thought generically local Hamiltonians should be gapped. Anyway, so I proved it recently that generically they're actually gapless. And I won't talk about it today. So you impose locality, and you take the local terms to be, random or generic. And yeah, as n goes to infinity. Thank you. Yeah, so all finite systems are gapped because you have a discrete spectrum.
Sorry. When you talk about generic, you need to focus about distributions.
Yeah, so I'm not, but yeah. So there in the paper there are assumptions, and So take the local terms to be from GOE, say. All right. Or actually, you can prove it for projectors as well, and other things. But I'm not going to get into the details. But the local terms taken from a fixed distribution with bounded moments. Just course summary. And I'm also very fascinated by the eigenvalue distribution of such matrices when the local terms are random. For example, as you get in spin glass theory, quantum spin glasses. But I won't be able to talk about that either. There's some video lectures of this, not at Simon Center, but at the Perimeter. But today, I want to talk to you about the ground states and entanglement of a little bit generic stuff, but then about some very specific models. And the reason we talk about these specific models was motivated by some generic questions.
This MIT chemist, is it Busik or what's the name?
Van Voorhis, bunch of postdocs, MIT chemists. We applied I think the person you're thinking about might be at Harvard. Yeah, okay. Very distant, very distant. So the problem is so difficult here that, forget about general quantum Hamiltonians. From now on, we're going to talk about one-dimensional spin chains. Okay? So this is a one-dimensional spin chain. There are d states per site. And if spin is s, d equals 2s plus 1. If you have a spin half particle, there are 2 states up and down. There are n particles. And this is a local Hamiltonian. So you see j and j plus 1 interact. And there's no interaction on every way to the left and right. And it's some of these terms. Moreover, every one of the local terms, since it acts on the tensor product of d and d, is a d squared by d squared matrix, right? We all know this, right? So then you can ask, well, generically, suppose you take these local terms to be generic, say. By generic, I mean random projectors, or you have, from a Gaussian ensemble, what do we know about their ground states, etc.? So it turns out that if the rank of the local terms is less than or equal to d squared over 4, all right? So if the rank of the local terms is less than or equal to d squared over 4, there are exponentially many frustration-free ground states. This is something we could prove in 2010. And if that R rank is yet less than d, there exists product states. But this is and moreover, with a graduate student, I could prove that if the rank is greater than d squared over 4, there are actually no frustration-free ground states. I mean, everything is with probability 1, right? Because it's generic. Exactly. So if the spin chain is length n, there is some constant fraction of all states that are ground states, zero energy ground states. Thank you.
And what did you say was probability 1? You referred to the thermodynamic limit?
In the thermodynamic limit and also with probability 1, because these are generic local distributions, you can always pick them to be very contrived and get something else. Okay. And actually, most of the examples I'll tell you about go the other way. They're low dimensional. So, we believe, now this part is not proved, we believe that between R equals D, and so if R is less than or equal to D squared over 4 and greater than or equal to D, which is really a meaningful bound after D equals 4, we believe that these ground states are all highly entangled. We believe it, but we haven't proved it. Now you might say, well, how do you prove such a thing? One way to prove it, there is a very simple idea from algebraic geometry, is that you find an example. If you find an example of a local Hamiltonian in this range, that gives you the entanglement bound, entanglements in the Schmidt rank sense that you want, you're done. Because there's a dense open neighborhood around it, and you can argue that it's full measure. All right? Now, so you say, well, let me build an example. So this argument is made more crisp in my thesis if you want to look, but it's really just that. If you find an example, there must be a neighborhood around it. So you might say, well, let's build some examples. Maybe we can figure out an example. So we started thinking about examples. Sergey also started thinking about examples. But these examples all went the wrong way. They all were we built frustration-free examples, but they were too high a rank. But these examples with time got more and more interesting, that at some point they took a life of their own. So now we have these exactly solvable models, and we don't refer back to this picture anymore. Because they all go the wrong way, but they've become sufficiently interesting that they started violating area laws. super critical area law violations, etc., that people just became interested in these examples for their own sake. Like, I don't go back to this picture anymore as often. I've given up on it. But I thought I'd bring it back. So what is entanglement? Entanglement is when you cannot write the joint state as a product state. Everybody knows this. I'm the brother of everybody. There are many measures of entanglement. One is the entanglement entropy that we've been hearing about. And although entropy generically actually scales extensively, so with the volume, so if D is the spatial dimension and L is the linear size, you would expect L to the D. That's a volume law. But we've been learning about area laws from physicists, that because of the locality of interaction and locality of correlation functions, most of the action is at the boundary. And you expect that for gapped systems that have massive excitations, you expect that the entanglement entropy of a region would scale not with the volume or all the degrees of freedom inside, but with the area of the boundary. All right? And it's called an area law, which is really an area in 3 dimensions. But area law means just that you go with one lower dimension. The name came from black hole physics probably and stuck. It should really be called a boundary law. And if you have gapless systems, we have good reasons from 1 plus 1 dimensional, well, don't look at here. We have good reasons from 1 plus 1 dimensional critical systems describable by conformal field theories. So some earlier works by Wilczek and colleagues, then Vladimir Koropin and colleagues, and then more recently Cardi and Calabrese. So they've taught us that the entanglement entropy in that case would be logarithmic. So for conformal field theories in 1 dimension, it's a fairly robust set of arguments that says you should have logarithmic amount of entanglement. Moreover, I want to emphasize that this claim has only been rigorously proved only in 1-dimensional gapped local systems with a unique ground state. All right? Rest of it is beliefs of various strengths. And this was the work of Hastings. So clearly, if you put D equals 1, you get 0, which means L to the 0 is 1. So it's order 1 amount of entanglement. And but this is for physical systems, right? So I want to define the rules of the game, like Israel called it, rules of the game. Rules of the game are that we want a local Hamiltonian, because if I have a global Hamiltonian, just take one random matrix, its eigenvectors are Har, its ground state is Har, and Har eigenvectors are known to violate the area law maximally. All right? So take a local Hamiltonian. We want a unique ground state. If you have high degeneracy, you can do funky things. And impose transition invariance, at least in the bulk. So these are the rules of the game. Within these set of rules, there was a strong belief that, whatever spin chain you can come up with will violate the area law maximally by a logarithm in the number of spins. So I changed L to N because, number of spins is proportional to L. So from now on, we're going to talk about N because we talk about spin chains. So this was the belief, and actually this belief was realized in a model that with Sergei Bravi, Libor Kaha, Daniel Nagai, and Peter Shore, we came up with in 2012. And it's a very nice model. Well, maybe I shouldn't say it's a nice model since I'm a co-author, but it's a decent model. People have liked it. It's a nearest neighbor interaction. It has a unique frustration-free ground state. It is unique. The half-chain entanglement entropy actually goes as maximally expected for such systems. It has translation invariance in the bulk, and the gap we could prove goes as a Oh yeah, this C has nothing to do with C. C generically means a constant. Hey. So the gap we proved goes polynomial. So it has to be gapless, right? Because the entanglement entropy is not a constant. It has to be gapless. But how does the gap close? It closes polynomially. And at the time, we could give an upper bound of, the gap closing as 1 over root n. So some, very competent physicists attacked us. They're like, only if you understood enough physics, you would know your model is really conformal. We would be like, we don't think it's conformal. They're like, well, you don't understand enough physics. So before I tell you that it actually is not conformal, let me tell you that there's a recent paper now that calculates. So this was put out in February or something. And actually, it was done here at Simon Center. This is where I finished it. So for that model, now we know a lot more. For example, we know we can write the Hamiltonian standard spin language. We know it has a U1 symmetry. The correlation functions have been calculated, so the magnetization x and y direction have been calculated. It's not for you to follow the formulas; they're in the paper. Entanglement about any cut, block entanglement entropy, Renyi entropies, and actually a entanglement Hamiltonian was identified. So we know a lot about this S=1 model. And my request for people sitting and not standing in this crowd is to find the continuum model. All right? There should be a continuum limit of this model that I don't know what it is. I believe it exists. It will not be conformal, so don't look there. It would be nice if somebody worked out a continuum limit of this model.
So what's the evidence that it's not conformal?
Because of this.
Because of what?
Because of in a later work, we proved that the gap actually closes as 1 over n squared. And this bound applies to the previous work as well, and it rules out conformal field theories, at least relativistic conformal field theories, in which the gap necessarily has to go as 1 over n, right? For the linear dispersion relation to be linear. Yes?
And then if the critical exponent is 2.
The gap, we believe, closes as 1 over n cubed, roughly. I think it might be 1 over n cubed, n squared log n, or n cubed log n. But we believe it's roughly like n cubed. And Adrian has done some numerics, DMRG, and I think he decided n cubed.
1 divided by n cubed.
1 by n cubed, yeah.
Your Renyi entropies are also not conformal.
These are exact. Everything is exact here.
They're not what you got in CF.
Oh, cool.
In the sense that if you would accept that that the entanglement entropy has that center charge, a little bit older.
Oh,
then
cool.
You want to know what the Renyi entropy scale like, and
Wonderful. Well, I'm not surprised. Yeah, it shouldn't follow conformal field theory. Good observation. Thank you.
So the equal time correlation functions, they scale with distance between the spins in some way?
Yeah. So the Sx and Sy are 0 everywhere.
Expectation value.
Expectation value.
Correlation functions.
So the
Sx at one point and
It don't
Sx
depend on the distance.
Right, they depend on the
On
distance.
the total size of the lattice, not on the distance.
Oh, not on the distance?
It's not conformal.
S- SCSC has been calculated exactly, and you basically get root n diminishing. So they lose memory of each other as 1 over root n.
And is the distance
Between the two. Between the two in the z direction. So actually, because of these boundary terms, you have these up and down 1 on 1, and it looks like, so it's kind of in the bulk dies out, but slowly. But the focus of this talk will be more the following, all right? So we came up with another model with Peter that violates that belief, not by log n, but by root n, all right? And this was surprising. And some other very good people got working on it. And 2 new results that I like very much. One is by Vladimir and Koropin and Sahlberger, and another one that you heard about by Klitsch and his students, Israel Klitsch. And they also get, so in their model here, they get root n, but they, instead of having an integer spin model, which is what we had, they have half integer spin. So it's kind of like a fermionic. With very similar features. So you get root n, etc. And Israel and his students basically, biased our walks to get n. But the interesting thing is that both these models didn't calculate the gap. Didn't obtain the gap for their model. Okay?
And there's also a theorem that can grow faster than that. Linear growth.
Yeah, I mean, maximum possible is n. That's right. I mean, maximum possible is volume, which in 1D is n. So let me just quickly review this Modskin walk business before I tell you about the Fredkin spin chain calculus gap. All right. By the way, I should say that this Fredkin spin chain, I think mathematically, I mean, quite apart from the implications for physics, the underlying Markov chain is very interesting. It's different from the things that usually fall into these universality classes we're used to. If I get a chance, I'll discuss it. So all right, guys, the idea is that for S=1, so this is the paper in 2012 with Sergey and others, you can label the 3 spin states, using +0, -, or what we like to use, which is a step up 45 degrees, flat and a step down 45 degrees. It's just a labeling of the spin states. And in the recent result that violates the area law with root n, well, we can take a step up. So here's a spin 2. So there are 5 states. You can take a step up that's red or blue, and similarly a down that's red or blue. In case somebody's colorblind, these are really 2 different colors. All right. Okay. And so the ground states will be uniform superposition of so-called Modskin walks. What's a Modskin walk? Well, it's any walk that starts. So this spin has the state up. This spin has the state down. So all together, they define some kind of a walk. And the type of walks we're going to have are going to be Modskin walks, which start at 0, end at 0, and never go below 0. That's a Modskin walk. If you take away the flat steps, it'll be a dick walk. D-Y-C-K walk. Dick walk. And the colored-Motzkin walk is the same, except that, a red, you can take a step that's red or blue, and red only balances red, and blue balances blue. For example, you cannot go red. So from here to here, you cannot do blue, red, blue, red. You have to do blue, red, red, blue. All right, so the ordering must match. Yes, yes.
So how important will the boundary conditions be?
Very important.
What if you release that?
If you release it, you can restore everything with a very mild external field that's uniform. That's part of the result that we have in the paper I just said with the root n entanglement, the PNAS I told you about.
In our paper, we have a bunch of boundary conditions. We use the boundary condition called Fredkin boundary. That's the difficult.
Yeah, no problem. So here, if you look in the model, we could actually get rid of the boundary conditions by adding a uniform external field.
What if you have periodic boundary conditions?
Well, then you use that uniform external field and everything works. Okay, so we can talk more. It's just that here is open with boundary conditions. You can remove boundaries, add an external field. It works. But if you want to close it, you keep the external field and close it. It still works. Okay. So let me give you an example of the ground states. So the ground state is a uniform superposition of these Modskin walks. If S equals 1 and you have only 2 spins, well, you can be flat, flat, or up and down. That's all possibilities. And if you have 4 spins, well, these are all possibilities, and there's 9 of them. There's a normalization. If the number of colors is 2, well, you can have a peak that's blue or red. All right? These are all possibilities for 2 spins. And, I could come and color these guys and, make another slide, but there's no point, right? So you see what I mean. So you can come and color these peaks, preserving ordering. And the Hamiltonian, I'm going to tell you the Hamiltonian now. What it does is that it basically implements the following moves, which means, it treats them symmetrically in the ground state wave function. So think of the flat step like vacuum, and step up as a particle, step down as an antiparticle. So a particle or an antiparticle can go through the vacuum. So you see the exchange position. They're symmetric. The ground state is symmetric with respect to them. But if a particle and antiparticle reach each other, they can go to vacuum or vice versa. From vacuum, you can create a pair of particle-antiparticle. And the way you implement these local moves is that you project out the antisymmetric space. So you give an eigenvalue 1 if the ground space, treats them antisymmetrically because of this minus sign. And to penalize, so when there are colors, I should also say here, I should have all these repeated for the red steps as well. But, so blue and red, they have the same projectors. And if a red reaches blue, you get a penalty because ordering must match as well. So I'm repeating what I just said. So these are the projectors now. And with these, without boundary conditions, you have a lot of degeneracy in the ground state. Actually exponential in the colored case. And in the uncolored case, it's linear for periodic boundary condition and quadratic for open boundary conditions. Yes, yes.
I mean, this sum of project, each project you can multiply by a positive number, right?
That's right.
So
that's right. Here's a robustness.
You keep the ground state. You might change the curve or something.
Yeah, that's right. Yes, thank you. Yes, indeed. So there is the projectors as local terms have a robustness against perturbations because, as Vladimir just pointed out, you can multiply the projectors by positive constants, even random or what have you, but positive, and preserve the ground state because the ground state is a zero energy state for frustration-free models. Okay, and for frustration-free projectors. And so to rule out the degeneracy and get a unique ground state, we add these projectors at the boundaries. So this dot, dot, dot means different colors. So red, blue, and you might have S equals, yeah.
Can we come back to the slide?
Yeah.
So for the last projector, why you each red, blue?
Oh, it's also there. I just didn't write it. There's also red, blue, and if there are more, and there are also the red version of all of these. So I should have said that, but I decided that not to make this slides too crowded. But yes, thank you. So here we project. So a Modskin walk is a walk that starts with an up step or a flat step, right? Never a down step. So you penalize, and you penalize anything that ends up with a step up because a Modskin walk should always go back down to 0. And this picks out the unique ground state. This picks out a uniform superposition of all Modskin walks as the unique ground state of that Hamiltonian. Zero energy unique ground state. And it has the features we want. It's a nearest neighbor Hamiltonian. It's translation invariant in the bulk. Why bulk? Well, because we have boundary projectors. It has a unique and frustration-free ground state, the half-chain entanglement entropy, and everything has been calculated rigorously, right? The constants, everything has been worked out in the paper. Goes as root n log s. So at s equals at least 2, you get root n violation. And the gap is polynomially small with an upper bound of 2. So it rules out conformal field theories as possible continuum limits.
So if I have periodic boundary conditions, so you can, there's some modification that also gives a unique ground state?
Yes. So I didn't include it here, but you can add an external field.
What is that like in that height space?
So you would have an added term at every site, and you would get a positive. You would give. Wait, what do we do? You penalize. I'm trying to think. So I have this slide. If you want to, I don't want to do this, but because I have a lot to cover. There we go. So yeah, you penalize step downs. All right, you penalize step downs, and that gives you what you want. All right, so that's the talk.
You lose frustration freeness.
You lose frustration freeness. Thank you. Somebody said that. Yeah, you lose frustration freeness, but frustration freeness is not a physical requirement you want to hold on to. It's nice to have, but it's okay to have a frustrated model as long as you preserve everything else. Yeah.
About translation invariance, you refer to the translation invariance of the bulk terms in the Hamiltonian.
That's right.
But what about the state? If you let the boundaries go to infinity, it converges to a unique state that is translation invariant, or?
No, the state is not translation invariant.
Not
No. It starts at height 0 and in the middle has root n, so it's.
So it has then at least.
It has a
ground state proportional to the length, so to speak. I mean, it's not sort of.
There's-
You count to the final volume, but it's supposed to. You won't converge at all, or you want to converge to a family of states that sort of have a mountain.
Антиодик boundary condition, open boundary condition.
It's unique.
It's unique.
As long as you have the project.
You can tell me the answer there.
Yeah, no. If you have an open chain and you keep the boundary projectors,
Yes.
and you have a unique ground state,
One.
unique frustration-free ground
But I
state.
take the limit. What is the result? Is it a pure state, or is it the
You can-
superposition of many things?
I think it's a pure state with a unique ground state as n goes to infinity. I mean, I don't know if there's a subtlety I'm brushing under the rug as taking n to infinity, but none that I see. It should be a unique ground state.
And then it is translation invariant because of the bulk model is translation invariant.
It's looked upon by local things, right? So you look in a vicinity of 100 sites, and then you let the boundaries go to infinity. That could still be translation.
If you take a section of it, it'll be a random walk, yeah.
Small subset, some small integral.
Right.
Well, I'm asking
Because
whether
you see,
it is.
the fact that the Brownian motion grows, if you zoom in,
Yeah.
you lose that. So I think it will be translation.
Inside.
What is the
inside
element
bound.
of smaller
No, I was just interested. I mean, he
So-
thought about a lot about his model, so I first wanted to know what.
Yeah, so so the thing, so if you cut a piece in the middle, say, and you let the boundary terms go to infinity, you effectively see a Brownian motion.
But the entanglement will be
It'll be still log L. So in the limit where L is much smaller than n and much greater than 1.
almost what was
No, log L for s equals 1 model and colorless. For the colored case, with a high probability, it'll be root L. But it's possible with a very low probability to have L step-ups altogether, in which case it's a product state. But with overwhelming probability, you'll still get root L as your entanglement ring. Why? Because the expected height, maximum or minimum height, of a block of L spins by Brownian motion ideas is root L. So there will be root L parentheses or root L steps that will not get matched within the interval, but they get matched outside.
In this Brownian motion idea, it would rather suggest that this state is a very mixed state, which is necessary
does.
for the entanglement.
That's right.
But so do you know whether it regarded as a state of this infinite chain is a unique state or whether it's also mixed?
So I guess I don't quite understand your question.
Well, I mean,
Yeah, it's
the chain length goes to infinity, the gap closes. So I mean, the infinite chain.
if you take a section of a unique state, so you have a unique ground state, you take a section, and you get a mixed state. And so
you leave it a translation variant state in the limit, at least that.
of that section, of a section, when you trace out two sides,
Then I can remove the section and everything will look the same.
you can within the limit that you're in the fluid limit, so to speak. So this block is much smaller than the system size. If you get too close to the boundaries, you're not in this limit anymore. Okay, we can talk more maybe. Yeah, fine, sounds good. So I want to talk now about the Fredkin Spin Chain and its ground state, which is a very recent work. It was posted maybe a few months ago by Vladimir and Sahlberger. So Fredkin Spin Chain. Anything else I wanted to tell you at this point? No. So Fredkin Spin Chain is the fermionic version. So you don't have flat steps anymore, and that gives D even and S equals. D equals 2s plus 1, so you have half integer spins. If D equals 2, like electrons, you have a step up or a down. And if D equals 4, you can have step up of two different colors and down of two different colors. Okay? Great. And well, what kind of ground state do you want? You want dick walks. Previously it was Modskin walks, you remove the flat steps, you get dick walks. This is called a dick walk. So you start at 0, end at 0, never go below 0, and blue matches blue, red matches red. Okay? And the ground state is a uniform superposition of all these dick walks, colored dick walks. Previously it was all colored Modskin walks. And the local moves, now these local moves are very interesting for more than one reason. One is that if you have the colorless case, you cannot have a nearest neighbor interaction because there's a theorem that tells you cannot possibly have any entanglement if you have frustration-free ground state. If you have frustration-free ground state on s equals a half, there's a theorem that forbids you to have any entanglement whatsoever. So they could circumvent that and get logarithmic amount of entanglement in the colorless case by coming up with a 3-local Hamiltonian that implements the following move. So any peak can go through a step up or down. So you see, I exchange this peak with a step up. You get this. Or a step down. Any peak can exchange with a step down. You get down and a peak. All right? And so it's really that simple. It's a very simple Hamiltonian. It gives you a lot. And you can naturally write the Hamiltonian. The cross and the boundary terms are exactly just like before. So you penalize the same way, and so the cross term is only meaningful when you have colors. Red and blue cannot get a penalty if they reach each other. And this is a 3-local term that implements those moves like I just said. So you have up, up, down. So there's an up and an up, down is a peak. Any up, down is a peak. So it just does exactly what I showed you in the previous step. And there's one more step where you can, if you have colors, now a peak of a blue color can go through any step up of whatever color, and a peak of blue color can go through step down of any given color. And there's a term that changes coloring from red to blue to green, depending on what the half integer value spin is. Okay? And, or fine, you can write the Hamiltonian in the colored case as well. This is there's no point, right? You can look, so yeah, look, up, down are of the same color, K2, and this up is of different color, K1. And it implements the same thing, except that you do the color code on the step up and down. So they didn't calculate the gap. So today I want to calculate the gap. To calculate the gap, there are 3 steps. One is that we're going to prove a polynomial bound. So the gap closes as 1 over n to a constant, where that constant is at least 2, just like the previous case. To do that, you need an upper bound on the gap, which you can obtain by multiplying. So without these phasors, you would just have the ground state. And with these phasors, you can use, so phi h phi gives you a bound, gives you an upper bound. That's how you get upper bounds. You can guess a state. And with these phasors, whose dependence in the exponent is on the area under the deck walk, just like the previous case. So with the colored Modskin walk, we also use this to get an upper bound. You get a 1 over n squared upper bound. And the mathematical ideas used are universality of Brownian motion and convergence of these deck walks to Brownian excursions. Brownian excursions are like Brownian motion, but they start at 0, end at 0, and they don't go below 0. A Brownian bridge can go below 0. So it shows that their model also is not described by conformal field theory. And to get a lower bound, there are 2 steps. One is that, above the zero energy ground state, what is the distance to the first excited state? That we call the so-called balanced subspace. And there, so there's a new Markov chain result I proved for this paper. And I think, again, the Markov chain mathematics of it, this Markov chain is interesting enough on its own, irrespective of the application for this spin chain business. Using the technique of the comparison technique, so most of the previous techniques we had, I hammered really hard at them. They just would not give. So something new was needed. And this comparison technique, along with the previous result, helped get the bound we wanted, a lower bound of 1 over n to 13 halves. So the lower bound is 1 over n to a 13 halves in this balanced space. And then that's not enough. You also need to show that the ground stays in the imbalanced state. So when there's actually a mismatch or a crossing of the colors, that the energies there are not exponentially small. And to do that, use perturbation theory and the previous techniques we actually used, the canonical path technique and the projection lemma. You can map the Hamiltonian into an effective hopping Hamiltonian and write down the ground state exactly, analytically, and bound its energy. Okay? That's the other piece. I won't have time for all of them. Maybe I'll have time for some of them, but I won't have time for all of them. And what I'll do today, I'll just tell you this very new piece, because the mathematical techniques here and here are similar to what we had before. They had to be, worked at to work, but this is mathematically also new, so I'll talk about this. Okay? All right, so we talk about the lower bound of the gap. Upper bound, take it for granted. So there is a technique, it was mentioned a couple of times in the previous talks, and in particular the previous talk. So if you have a frustration-free stochastic local Hamiltonian, I just realized actually in remark 2 of this Fredkin Spin Chain paper I put out, there was a spell checker changed all the stochastics to stochastic. So don't get confused if you read it. Remark 2, page 10. Those should say, because it says in particular stochastic matrices can have diagonal entries of any sign. No, because I'm comparing them to Markov chains, which should have non-negative. Because these stochastic matrices resemble a lot continuous time Markov chains, and there's a beautiful connection I'm fascinated by between these two. So you can grab your Hamiltonian. This is the induced probability distribution. So stationary distribution Markov chain language. And beta is just some parameter that you tune to make sure that the Markov chain on the left-hand side has row sums equal 1, diagonal entries that are positive, etc. So it's I, the identity matrix, minus beta times this piece. And the cool thing, really cool thing, is that now, because of this minus sign, what used to be the gap of the Hamiltonian, the difference between the two smallest energies, becomes the difference between the two largest eigenvalues of P. Right? Because identity, if you add identity to any matrix, you just add 1 to every eigenvalue. That doesn't do anything. But this minus sign will switch the order of eigenvalues. And that is really great because in Markov chain community, what you bound is exactly the distance between the two largest eigenvalues. So if you can do this mapping, now you can make use of the literature in Markov chains. All right? So the mixing times, the spectral gaps, etc., in the Markov chain community can now be used to bound the gap as we know it in quantum many-body systems. Yes. So maybe I make one more remark. Yes.
I thought it was much harder to prove bounds for Markov chains than for Hamiltonians.
Really? Okay. I don't know about hardness or easiness, but the point is that you can utilize what exists in the other community, in Markov chain, regardless of how hard it was obtained.
Well, I think in this stochastic case, it's really still a problem of silver.
Yeah, you just map one to the other. Yeah. In this case. So the good thing is that you can, if this Hamiltonian has some kind of combinatorial interpretation, you can map it into local moves that can be seen as a Markov chain with local transition rules, and then you can see whether you can get some mileage out of the corresponding Markov chain. Okay. So one other thing I want to say: the gap in quantum many-body systems is the difference of two smallest eigenvalues, right? The gap in the Markov chain is the difference of two largest eigenvalues. The gap in random matrix theory is the distance of eigenvalues in the bulk of the spectrum, not the edges. So you see the meaning of gap, and I've seen this confusion a lot talking to colleagues from different communities. It can be very confusing. Like sometimes you talk to colleagues in physics, they're like, well, the gap is universal. It was proved in random matrix theory. But what they don't realize is that what they call the gap is useless for us. We want the gap, the difference of the two smallest eigenvalues, not some rigidity result in the bulk. So this, if you write in the matrix notation, you realize this is similarity transformation. Right? So the gap, there's a simple, the largest eigenvalue of a Markov chain is always 1. So this is the second eigenvalue, 1 minus lambda 1 is the gap of the Markov chain. You multiply by this constant factor, so beta turns out to be this constant factor for us to make this the Markov chain we want, and that gives you the gap of the Hamiltonian. So what we want is the gap of the corresponding Markov chain, because then we're done. It goes into being able to do all of this. So if you look at this paper, it goes into being able to make this mapping from beginning. So here I just wrote down the answer. But to be able to interpret these guys as probabilities, this, get a beta such that this becomes a Markov chain, etc., you need that. So the corresponding Markov chain is the same rules as I told you before. So this is the uncolored case. Now, check out one thing, right? So here I move the peak to the left of this step, right? Now in your head, flip this peak. So flip it downwards, you get the same picture. Or flip this valley upwards, you get the same picture. Similarly here, if I flip this downwards, you get this picture. And if you flip this upwards, you get this picture. So it resembles this Markov chain. Whenever you see a peak or a valley, flip it. This is called card shuffling with adjacent local rules. So if you have red and a black color, step up or down, shuffle them. All right? And that's what this does. And this card shuffling business has a long, has a fairly cool literature. And this card shuffling, there is a tight bound on the mixing time. So the lower and upper bound is n cubed log n. And mixing time and the gap are related within a factor of n. So we have sharp bounds on the gap.
What about this positivity?
Okay, good. So card shuffling has a couple of problems. The biggest problem is that you see here, if you have a valley with a side length of at least 2, the card shuffling will flip it, right? But the Fredkin Markov chain doesn't do anything. And you might think, well, you know, you can circumvent this. And it turns out this really kills it. Like if I tried really hard to make this work, you know, all sorts of comparison techniques, canonical paths, etc. The edge loads I would get, which I wanted to be polynomial, would always end up exponential because of these suckers.
If you translate this to spin chain language, this would essentially correspond to the Heisenberg XXX.
What would? Oh, this. Yeah. Okay. Yeah. Cool. And
Or from the point of view of card shuffling, so I have a deck of n small cards, and tau is the time to mix it to turn into stochastic.
okay, so good.
Game, right?
Yes. So you have a card of black and red cards, right? And the question is, grab 2 cards adjacent to each other. If they have different colors, swap them. Okay. Now then you can ask, what is the minimum time it takes for this deck to be well shuffled? And what does it mean to be well shuffled? It means the next time you draw from it, you draw from a uniform distribution or the stationary distribution. Right? So it's the expected time to mix it such that the next time you draw from it, it's epsilon close to the stationary distribution. Thank you. So anyways, so I just wanted to tell you that I had some failing times with this thing. So looking at various techniques to prove the mixing time, so Frank, this is a case where you could actually prove using Markov chain stuff. I couldn't do it based on just looking at the spin chain. So there is a theorem called comparison technique, which I'll describe in a second, which says the following. If you have the gap of one local, so from now on I'm going to talk about Markov chains, right? Divorced from quantum mechanics, because, you know, we just established that the gap of the Markov chain will give us what we want. So there is a comparison technique that says if you know the gap of a model, and there is a way to compare it, relate it to the gap of the unknown model, then you can bound the gap of the unknown in terms of the known. That's very vaguely putting it. I'll make it precise in a second, all right? So I have 2 Markov chains that have similar features. I know the gap of this. Maybe I can use this gap with some polynomial constants to get the gap of this. That's comparison theorem. So since Wilson's card shuffling didn't work, going back to the roots, we proved the result. We proved the result in these papers where suppose you have the following Markov chain instead. It looks on the deck walk. It picks a random position on the deck walk of length 2n, and if there's a peak, it chops it off and inserts it at a random position. So here I chop this off. Look, the height is lower, and inserted it right in the valley here. Okay? That's a Markov chain. And we could prove that the gap of this Markov chain goes as 1 over n2. So there's an s in case there are colorings, s different colors. Goes as 1 over n to 9/2, and there's a root pi, whatever. And this was done using the so-called canonical path technique that in the earlier paper we used, as well as this root n. It's a technique we've been using. So there are various things. And also, like, we proved a new result in statistics of dick walks to get these bounds. So we have the gap. Think of p tilde now as that Markov chain with a known gap. Tilde means known. Untilde means unknown that we were trying to get. There's a comparison theorem that says, suppose you have 2 Markov chains, one with a known gap and one with the unknown gap you want to bound. All right? This is what we want to understand. If you can get the following factor A by a way of choosing paths, I'll tell you how to choose paths. So if we can quantify this quantity A, then you can actually get the gap of the unknown in terms of the known. Now, what is this A? This A basically says, so you grab two. So this is the known case, right? This is an adjacent move, one adjacent move in the known Markov chain. Cut a peak, insert at a random position. This is the known case. But with the Fredkin Markov chain, you can't do this. This is not a transition in Fredkin Markov chain. If you can relate this move to a series of moves where you start here and end it here, using moves of Fredkin Markov chain, that's called a path. So how can we do this? So here, I can grab this peak, move it to the left. One space. It's just like flipping it up and down if you do it in your head. So there's a step up and an up, down. I move the peak to the left of that step. I get this. Now I move this peak one more step to the left. Okay? And I do it yet again. And I do it yet again, and I'm home. Okay? So with a series of moves in the Fredkin Markov space, I got where I wanted to. Now the only thing you have to ensure now is that any one of these intermediate edges is not used by many such paths. So these are two arbitrarily x0, x and y. Suppose I look at all x and y. I should be able to do this for all x and y. I should make sure that there's no edge whose maximum load, meaning all other paths going through, is exponentially large. But that is not hard to show. The thing is, if you think in your head, the Markov, the path you're free to choose. The path is something you have freedom to choose. Take the following path. So the Markov chain takes a peak, inserts it at a random position. The path is defined as following. Take this peak, use your Fredkin Markov chain to move the peak all the way to its final position. Okay? So two adjacent moves in the known case is related by walking a peak all the way to its final position. Okay? The length of this path is at most 2n, because that's the size of the chain. This peak could have started in at most n positions and terminating at most n positions, let's say 2n positions. So there's an n cubed factor altogether now. And if in the case that there's coloring, move the peak of any given color to its final position and change the color at the last step. So that's s possibilities. So that gives you everything you want. You plug it in. So here I made the simplification because this pi of x and pi of z are uniform on the space of Dick walk. So you can just cancel them out. Anyway, so you put that in here, and you get the lower bound you want on the gap. Upper bound on the mixing time gives you a lower bound on the gap. So you get minus 13 halves. And the upper bound on the gap we showed before was 1 over n squared. So we're done. There's a polynomial gap on the Fredkin spin chain. So Israel yesterday described the model where you get n amount of entanglement, and intuitively, and also as he said in his lecture, intuitively would expect an exponentially small gap, but we have proved now that actually the gap goes as e to the minus n squared. It's kind of like the area under, not using these techniques, using other stuff. No, it's just C actually. It's some constant. You can show that it's exponentially small in the area. Positive constant, yes. Didn't I say that? No, I didn't say it. It's a positive constant. Yeah, that's right. Well, wouldn't it be cool if it were actually negative? So there are many open problems, entanglement versus gap. There's some results that say if you have a bound on the gap, that should say something about how much entanglement you can have. So really distill that out, and this would really be, since we talk in terms of bounds, this would be really a nice thing to do for someone like Adrian who does DMRG. He can really nail down these exponents. And he's done so in the past for a few of our works. He can really give you the exponent. So when there was an external field, he got 8/3. With the boundary conditions, he got the 3. So it made us very certain that these exponents we had intuited were correct. Implication for simulability and just easiness of 1D chains. We need higher dimensional models, so it would be really great to have exactly solvable higher spatial dimensional models. And I personally am really fascinated by this connection between quantum local Hamiltonians and classical local stochastic Markov chains or Hamiltonians. There are various ideas, some that we touched on today, but there's ASEP ideas as well. Heisenberg chain can be thought of as an ASEP. I think there's just something really nice underneath. Maybe it's known entirely, and it's just fascinating to me because I haven't caught up to it. But I also feel like looking at the probability literature and the talks, etc., the frontier, it seems to be a fairly active frontier. So I think there are some really interesting things to be done here still. Yeah, people in the probability don't understand quantum mechanics that well, and we don't understand their work that well. Anyway, so with this, let me just thank you and take some questions. All right.
Questions for friends?
Yes.
Know about the density of states above again?
No, but exponential, I would say, for the colored case.
Well, that's probably more relevant for the area law than somehow the gap itself. How many states are close to that?
So that's really a question for your neighbor to really nail down the density of states. But since the degeneracy is removed by these boundary conditions, and the degeneracy in the colored case is exponential, and these boundary terms have a constant norm, and the Hamiltonian can go to infinity, you would strongly suspect that the density of states near the ground state for the colored case is exponentially large. And in the uncolored case is linear or n squared, depending on whether you have open or closed boundary. But there you only get logarithmic anyways, in the uncolored case. Yeah?
About the density of states, you have an exponential number of states which are
I think so, yeah.
Written down. So this kind of scaling to the minus n squared.
Oh, for your model. Yeah, I see. I don't know what the density of states nearby is actually, because you're weighing the. But your model is not the same, right? Like, so instead of taking a uniform superposition of all Modskin walks, is not the case. I mean, you really where do we get root n from? Like you said, this ordering is what carries the day, right? So not only that, yes, all random walks have root n expected height in the middle, but when you color them, since the ordering has to match, that gives you a lot of mutual information, and that's why you get actually root n. Or you can think in terms of these singlets going to the sides. Yeah, but in your walks, you don't have everybody. You actually bias it so you get taller heights, so that root n goes up. So it's intuitively not very clear for me to be able to scale. But I want to say the following. In the Fredkin case also, you can bias the moves that increase the area and push them, and then you get also. And please, yes.
So at the beginning of the talk, you mentioned this conjecture about random spin chain
Yes.
and ground state entanglement. So there was this intermediate region, and the rank of projectors is between B and is the over 4.
Yes.
So have you get any insights into these conjectures using this Fredkin spin chain?
So the right. So first, let me say what the conjecture is. The conjecture is that the theorem is that there are exponentially many ground states. The conjecture is that every one of them is highly entangled in a Schmidt rank sense. So exponentially many. The Schmidt rank is exponentially large. And we need a single example. All these examples go the wrong way. Right? Why do they go in the wrong way? The reason is that the rank is too high. Even in the Fredkin case, when you introduce colors, those cross terms give you like n choose 2 number of terms, right? Because you have red, blue, So in the colored case also, that pushes the rank really high up. And that's why, these examples don't really address, what we wanted from the beginning, but they're interesting for their own sake. Okay. We need a low rank local Hamiltonian. Comments? Sure. Let's maybe go back to your question that you were pressing on.
If you look
maybe you guys can help out too, if you understand the question.
Observable. You look at something local, a finite piece of the chain.
So by local, you mean really local? You mean just to take a
fixed scale, and I'm going to let the boundaries go to infinity, but I can let it go to infinity in different ways.
Sure.
Maybe it goes faster to the right than it goes to the left. This sort of corresponds that maybe I can fix this little piece in the middle, or I can let it go off as my chain grows at some rate.
Just far from boundaries.
Yes. It's the remaining part of it. So do you always get the same limit, you think?
What limit? Limit of what?
Well, as the state. I look at the state, this
Okay.
local state.
Okay. And what do you want to do?
I just go to infinity,
Okay.
these values raised, you get the same limit.
Same limit of what? The ground state being the same?
Any expectation.
Any expectation. So,
Try to fight with it.
okay.
It's not, okay,
No, it's not.
let's take Israel's idea. So the weight will be T large number
To the
raised
area.
to our area. Let this number go to infinity. Really large is a real parameter. Then the only one dwarf will contribute to Modskin or just the mountain.
Yeah.
Go up, go down. If I translate it back to the spin, will be the left part of the spin, all spins looking up, ferromagnetic, and then spin down. And then your answer is not unique ground state, not unique ground state, because I can choose ferromagnetic piece with spin up, ferromagnetic spin down, or I can choose this middle with a flip. So in your sense, I guess it's not unique. That's why I attempt to fight with you.
That answers your question?
Well, yes, so it
Okay,
means
so
that
you're- okay, you're
translate-
happy.
Actually, translation variance may be broken in some of these models.
Yeah, that's
You can have a lot of...
I guess a question of language, right?
The state has spontaneous growth issue of translation. And this is an example.
The state is certainly global, right? The state is a global thing. It's not
That
a...
also means that you have to be very careful when you calculate your entanglement, because you can have limits that are mixed.
Yes.
Okay, I can continue this discussion.
Right,
Because
okay.
the walk-in upstairs.
That's all.
Thank you.